Hi everybody, this is lecture 10 and we are doing section 6.3. Now note that we're actually not going to do 6.4, but I'm going to mention it to you and sort of describe what they do in 6.4. But this section is all about solving around a singular point, or so finding solutions, series solutions around a singular point. Now last time in 6.2 we looked at finding solutions that were centered around an ordinary point of the differential equation. But now we're going to do the same thing for a singular point. So to understand a little bit more about what singular points are, we actually need to know how to classify singular points. So because it turns out that we're really only going to deal with one kind of singular point, and that is a regular singular point. So if we describe our differential equation as usual in the standard form, y double prime plus p of x, y prime plus q of x, y equals 0, right? Then we have a definition of what a regular and an irregular singular point is. Oh, R, sorry. 1 second, I'll pull it up. Okay, so I have the definition up here. So a singular point at x equal x naught is said to be regular, a regular singular point of the differential equation, this one here, if the functions little p of x, which is x minus x naught times px, and little q of x, which is x minus x naught squared times big Q of x, are both analytic at x naught. Now, if that is not true, this is called an irregular singular point. So that sounds like a lot of stuff going on. Let's take a look at an example. I think that would help a lot. All right, let's take an example here. So we have an equation x squared minus 4 all squared y double prime plus 3x minus 2 y prime plus 5y is equal to 0. Okay, all right. So if we divide the equation by this, like to get it into our standard form, right, we have y double prime, and then we have plus 3x minus 2 over x squared minus 4 squared, right, times our y prime, plus 5 over x squared minus 4 squared times y equals 0. So that's in our standard form, and we can see that this is our p of x, right? So p of x, let's see, let's write that down. So we have 3x minus 2, and then x squared minus 4. Now, x squared minus 4 can be written as x plus 2 times, and this is squared, sorry, x plus 2 times x minus 2, so we'll write that out. So we have 3x minus 2 over x minus 2 squared times x plus 2 squared. And so what we can do is just cancel one of these out, and we get p of x finally is 3 over x minus 2 times x plus 2 squared. Okay, what about q? Let's just write down q. So q is equal to this here, and we can't really do a whole lot with that, but I can factor at least it out into these two things. So 5 over x minus 2 squared, x plus 2 squared. All right, that's q. Now what happens when we multiply? See, it says here like this, x minus x naught. Now what does that mean? Well, if you think about it, right, there are singular points here, right? If you look at this equation here, you can see that x equal 2 is a single point, and x equal minus 2 is also a singular point. So we have the two singular points We don't know what kind of singularities they are yet, but we have the two singular points -2 and 2 are singular points. Right? We don't know what kind they are yet. That's what we're trying to do here, is try to test that. And so we have, let's look at what the test would be, right? So remember, it's little, so we're going to define these little p of x's. So we have little p of x. Oh boy. Okay, so I'm not going to be able to distinguish that. I better like figure out what to do here. Okay. So I'm going to put a little capital thing on this p of x here. Okay. Right, see, that's a little capital P of x. And the Q is pretty clear. All right, so little p of x is x minus x naught, and x naught is our singular point. So let's say x minus 2 times 5. So we're testing the x equal 2 point. Or actually, why don't we test the minus sign first? X equal 2. So x minus 2 is x plus 2. Times 5 over x minus 2 squared, x plus 2 squared. Okay, so what happens here is that we get, this will cancel out one of these guys, right? And we get little p of x is 5 over x minus 2 squared times x plus 2. Okay. All right, so if we notice here, we're looking at x equal -2. So if I put x equal -2 into here, I'm going to get it blowing up. So this is definitely not analytic, right? At x equal -2, okay? So not good. Now it says that both of them need to be analytic. Let's just, for the heck of it, so we already know that the differential equation, that the singular point x equal -2 is irregular. That means that if it fails either one of these tests, so it just failed my test with little p of x, I'm going to see what happens with little q of x, but it already failed. So I know it's irregular, but just for the heck of it, let's test little q of x. Little q of x is going to be x plus 2, x plus 2 squared times my q of x, which is 5. Oh, shoot. This was, yeah, I put 5 here instead of 3. Well, that was kind of stupid. Anyway, 3. I think I did everything else. Oh, sorry, that's 5. This one is 3, and I think I messed all this up, didn't I? Yep, I did. All right, let me just fix it. So I'm going to tell you what I'm fixing while I'm fixing it, because that way you can fix it on your paper. So notice that I just wrote down Q for P. It didn't matter in the end, but I just wrote down Q, except for I have, yeah, so here's Q. It has squares in both the bottom here. But so if we get rid of this, then and make this a 3, then we're still in business, right? Still in business. Sorry about that. So get rid of this. It's still, this is not analytic at x equal -2 for sure, because we have this term here. Okay, and this got canceled because of this guy, remember? All right, so little q of x is, we have to do the test where we go x plus 2 squared, and then we have 5 over x minus 2 squared, x plus 2 squared, and that whole thing cancels out. And notice that at x equal -2, right, so this is 5 over x minus 2 squared. At x equal -2, this thing is perfectly fine. So this guy is analytic at x equal -2, but since little p failed, right, the point is an irregular singularity. Okay, they both have to pass. Okay, because it says and both. Okay, let's test our next point. So x equal 2, and let's see if it's irregular or regular. I'm going to start with little p of x. So little p of x, I'm going to read the right one now. We're going to multiply that by x minus 2, right? So remember, it's x minus x naught. So x minus just positive 2 is x minus 2. Okay, we'll multiply big P of x, so it's 3 over x minus 2, and then x plus 2 squared. All right, well, that's going to cancel that, and I get just 3 over x plus 2 squared. And of course, at x equal positive 2, this is perfectly fine. So is analytic at x equal 2. Now, what about q of x? Because if it fails, then this thing is an irregular singularity. So let's see. So we have q of x, that's this, big Q, right? So we're going to multiply by x minus 2 squared. So x minus 2 squared. And then big Q, which is this, 5 over x minus 2 squared, x plus 2 squared. These cancel here, and we're looking good, right? 5 over x plus 2 squared, and notice if I put positive 2 in here, this is perfectly fine. So this is analytic at x equal 2. So this is a regular singularity. Okay, it's still a singularity, right? It's definitely singular point. So it's a regular singular point. And we are just not going to deal with anything but regular singular points. But you need to know how to solve for them. And in fact, we're really not going to deal with anything where our singular points are non-zero. So we're going to look at singular points that are x equals 0. Anyway, it's just easier. But to do the rest of the work in this section, we're not going to deal with irregular singular points. But you need to know how to test your equation for singularity. Okay. All right. Remember, singular points can be complex, etc., which we saw last time. Okay. So what we're going to do now is look at how to solve these equations to use series solution, where we're expanding around a regular singular point. And again, we're only going to use the singular point x equals 0. And we're assume or test that it's regular. Okay. Let me kill these layers. And that's going to stay. That's fine. Okay. I guess I could get rid of it there. All right. Let's look at a theorem that tells us about the existence of these kinds of solutions. Okay, this is called Frobenius' theorem, and you've probably heard that name before, very famous mathematicians. And he says that if you have a regular singular point of a differential equation, right, that one means, the second order differential equation we've been looking at the whole time, then there exists at least one solution of this form. And if you look at the form here, it's kind of funky. It says, you're expanding around a point. Again, we're always going to be doing around 0, right? We're, solving around this point. We're centering here. And we have, because we had an x minus x naught to the r here, we're going to have x minus x naught to the n plus r in this series here, right? So there's at least one solution that's going to look like this, where r is some constant that we have to determine, and that the theorem also says that the series will converge. I mean, it might be a small interval on some interval with a radius of convergence r. Okay, so you might be thinking to yourself, well, what's that r thing, right? Well, in fact, that r does not have to be an integer. So imagine if that r is, 0.25 or something, right? are -4. So if it was -4 when n equals 0, you're going to have x to the -3, right? That is not a power series. So you may end up with solutions, and very often end up with solutions that are not power series anymore, okay? Even though it kind of looks like a power series here, that r doesn't need to be an integer. I think the best way to get started here is just to look at an example. So let's look at an example of, we have the equation 3x y prime, y double prime, right, plus y prime minus y equals 0. Okay, so we're going to try to find the solution here, just like because of this theorem, we're going to try to find a solution that looks like this. Okay, so we're going to look at solutions that kind of look like that, right? So we have the sum n equals 0, and then we have Cn, and then it's x minus x naught, but we're expanding around 0. So I mentioned that we're just going to look at 0. And notice that 0 is a singular point of this, right? But by the test, if we multiply by x, right, so imagine you put this into normal form, you're going to get y double prime plus y prime over 3x minus y over 3x. If you multiply that p by x, right, it becomes analytic. And if you multiply by x squared, it certainly becomes analytic. So it's a regular, this is a regular, prove this to yourself. This is a regular, singular point. All right. So we're going to put down here just x to the n plus r. Okay, fine. So now we just need to do what we usually do. We just take derivatives, right? So we're going to go y prime is the sum n equals 0 to infinity, Cn n plus r, x to the n plus r minus 1. And notice here that when n equals 0, I don't get a 0 term. So I'm not going to change where I start the sum. Okay, so y double prime is equal to the sum n equals 0 to infinity of Cn n plus r minus 1 x to the n plus r minus 2, right? Okay, so this, again, is not 0 anywhere, right? It's not that it's not 0 when you have n equals 0, right? Not 0 when you have n equal 1, so I'm not going to change where I'm starting that from. Okay, so then we're going to substitute into our equation here. Okay, so we get 3, and then we get the sum n equals 0, and I'm pulling the x in all in one thing here, but we get Cn n plus r, and we get n plus r minus 1, and then we get x to the n plus r, and then minus 1, right? Because I took one of those off, because I pulled in the x, right? Okay, and then plus, I'm going to get just our series, the first derivative of the series, which is the sum n equals 0, Cn n plus r, and then x to the n plus r minus 1. Okay, cool. And then minus the series sum n equals 0 to infinity Cn x to the n plus r, right? And that's all equal to 0. All right. So luckily this one's nice. It has the same power here and here, and then we have the same starting point here and here, so we can combine that right away. That's really cool. So we get the sum n equals 0 to infinity, and then we get, let's see, 3 Cn n plus r n plus r minus 1 Okay, and then on this term we get plus Cn. I guess we could have pulled out the Cn too, right? Okay, whatever. N plus r. And that's all times x to the n plus r minus 1. Alrighty, and then minus this other term, so minus sum n equal 0 to infinity of c n x to the n plus r. Sorry, that looks like a v, r. And that's equal to 0. All right, so I'm going to actually pull out x to the r. Okay, so here it is, x to the r here and x to the r here. I can just sort of pull it all out. And I'm going to move this because I want to pull it over to this area. Oh, come on, move, please. Nope, all right. I have to do it with a regular mouse. Nope. Sorry, technical difficulties. There we go. All right, so I'm going to do it over here. I'm just going to write x to the r, and then I can write the series again, right? So I have sum n equals 0 to infinity, and then I have 3cn n plus r, and let's see, 3cn n plus r. What was the next term? Oh yeah, n plus r minus 1. That's that term, and then plus cn n plus r. All right, and then that's all times, that's got another parentheses here. Sorry about that. Let me fix that. This does not look good. And we need 2 parentheses. Okay, n plus r. Then we need another parentheses, so maybe we should do those. That's, you know, a nice square bracket. And then x to the n minus 1, right? Because the x plus r is out of here. And then we have also minus sum of n equals 0 to infinity cn x to the n, right? And then equals 0. All right, so I just pulled out that x to the r. All right, we're going to write one more time. I'm going to come down here. I'm just going to pull out a, notice here that I have cn and n plus r and cn plus n plus r here, right? So I can pull those out as well. I'm just trying to simplify it as much as possible before we move on. Okay, so we have x to the r, and then my large bracket, then I have sum n equals 0 to infinity, and then I have this, you know, square bracket, and then I'm going to pull out cn, right? So I'm going to pull out cn and then n plus r. So cn n plus r, I'm pulling out. Now I do that, what is I left with here? I'm left with a 1 here, and I'm left with n plus r minus 1. So that's just going to give me, and I think we're in my 3 here, right? So I'll get, let's pull the 3 in. So we'll get 3n plus 3r, and then minus 2, right? Because this will be 3 times minus 1, and this will be just 1, and I've got my little term here that I want. Okay, and then of course this is all times x to the n minus 1, right? So x to the n minus 1, and I guess I needed my bracket here, but okay, whatever. All right, here we go. And then minus the sum n equals 0 to infinity of cn x to the n, right? And that's all equal to 0. All right, so let's take a look at this. So when n equals 0, I get x to the minus 1. Okay, not very useful. Given that when n equals 0, I get x to the 0 here, right? Remember, I kind of like to have them both doing the same thing. So I'm going to take that first term, n equals 0, out of there. Okay, so I'm going to take x to the r here, and then I'm going to pull the first term out. So when n equals 0, I get c0 times r times 3r minus 2, right, times x to the minus 1. So I get c0 times r times 3r minus 2 times x to the minus 1, right? And then what I'm left with is plus the sum n equal 1 to infinity of my term here, right? Cn, and actually I don't need those parentheses. Let me not have too many parentheses, but I don't need them. All right. So then I have Cn, n plus r, and I have 3n plus 3r minus 2 x to the n minus 1, but now starting at 1. And now this starts at x to the 0, as does the other series. So that's nice. So you always want to try for that before you start manipulating your, indexes and changing to k and everything. Okay. So that's now equal to 0 here. So here we go. So this is going to start at the same place. So I'm going to let k, in this one, I'm going to let k equal n minus 1, which gives me n is equal to k plus 1. And this one, I'm just going to let k equal n. So I'm just changing my indices, which I'm free to do. Okay. So here, let's just write it all out again. So we have x to the r, c, 0r, 2r minus, 3r minus 2, x to the minus 1, and then plus, we have sum. Now so for n equal 1, right, k equals 0, so we're going to start from k equals 0. Okay, so we're going to start from k equals 0 to infinity. And then we have c k plus 1. We have k plus 1 plus r. We have 3 times k plus 1. So 3k plus 3 plus 3r minus 2, right? And we'll fix that all up in a second. And then we have x to the k. And then over here, I just have sum k equals 0, ck x to the k. Okay, that's looking pretty good. Okay, all right, so let's keep going here. So we have our series in a pretty decent form. Let me just rewrite this one term. If you look, it's all proportional to x to the k, and it goes from k equals 0. So one more time, let's write it all down. So we have our x to the r out in front of everything. And then we have our term c0r, 3r minus 2, x to the minus 1, and then plus sum k equals 0 to infinity of ck, ck plus 1. There we go. Blanked out there for a minute. It happens. Okay. And then 3k plus 3 plus 3r minus 2 minus ck, and that's all times x to the k. It's all in that sum, and equals 0. Now again, we have our identity property, remember, that says that if you have terms that are linearly independent from each other, that's really what it's saying, so I'm just saying it a different way, and all those terms add up to 0, then each of the coefficients of those terms, right, the x to the k, the x to the minus 1, and of course there's an extra r out here, are 0 themselves. Okay, what does that give us? Well, first of all, it gives us this guy is 0. So we have C0 R 3r minus 2 equals 0, and I can just get rid of that C0. And this gives me an equation for r, which is really cool. It gives me two solutions. Let me write them over here somewhere so I have a little more room. That's down. All right. Okay, so it tells me r equals 0 and r equals 2/3, right? So we solve for r, you get the 2 on the other side, 2/3. So remember that I said when we started this, and you can see up here, that r is a constant that will be determined. Well, here it is. Okay, it has two roots, and that is going to help us get the two solutions we want. Okay, now that is not always the case. I shouldn't make it sound like that's always the case. It is possible that you only get one, right? Linearly independent solution. Then you got to do some more work to get the second one. Okay, just FYI. But in this case, it looks like it's going to give us two solutions, because what I can do is write my next thing, which is that this whole thing is 0, right? So that tells me that, let's see, am I going to write it as my recursion relation? But I can just write it out first. So I have k plus 1 plus r times 3k plus 3 plus 3r minus 2, and then minus ck. Oh, my ck plus 1, how could I leave you out? Okay, here we go. Minus ck is equal to 0, and that's going to give me a recursion relation. But notice that I have two values of r. So I can put one r in here and get one recursion relation, and put another r and get a second recursion relation, and that's exactly what we're going to do. Okay, let's do it. First I'll write them down, and then we got to go to a new layer. I might just erase because it's kind of a mess, and it might be easier just to keep this stuff down here. All right, so for r equals 2/3, so we'll just pick that one, we get ck plus 1 is equal to ck over 3k plus 5. Wow, that looks like alpha. 3k plus 5, and then k plus 1. And of course, k starts at 0 here, right? Remember, our sum tells us where we have to start. So k equals 0, 1, 2, dot, dot, dot. And then for r equals 0, right, I have a second recursion relation, so a different one. Ck plus 1 is equal to ck over k plus 1, and then 3k plus 1. So totally different. And of course, again, k is starting from 0, dot, dot, dot. All right, let me erase some stuff. I'll be right back. All right, so we're back, and I put the two values of r here so you can see them. And here's our equation that led to the two values of r, and here's the original series that we're using as our solution. And so what we're going to do is just implement these recursion relations for r equal 2/3 and r equals 0, which we already put in the values of r. Okay, so first we have c1 is equal to c0 over 5. And over here we'll have c1 is equal to c0 over 1, right? Oh, we're starting from k equals 0. How silly. Okay. Yeah, so I over here I just was looking at this and thinking, wait, why is it 1? Yes, it's 1, right? Because k is 0, right? And you get 1. And over here k is 0 and you get 5, right? Okay, so we're starting at k equals 0, even though this gives us, of course, ck plus 1 is c1. All right, c2 is c1 over 8 times 2, but that's just c0 over 2 factorial, and I'm writing it this way for a reason, but times 5 times 8. Okay. Over here, I get C2 is, and I'm going to skip steps, so hopefully you can go and figure this out. It's 2 factorial times 1 times 4. Again, writing it this way for a reason. C3 is C0, so I'm going directly to C0, right? Because of course C3, you'd have a C2 here, but C2 is this, right? And so you'd substitute in, okay? Just skipping some steps in the interest of brevity. Okay, so hopefully you can verify all this yourself. So this is 5 times 8 times 11. C3 over here is C0 over 3 factorial times 1 times 4 times 7. Okay, and over here, C4 is C0. Again, I'm skipping, you know, because obviously it would be written in terms of C3, but C3's got C0 in it. Okay, so we've got, this is 4 factorial times 5 times 8 times 11 times 14. And C4 over here is equal to C0 over 4 factorial times 1 times 4 times 7 times 10. And then we're just going to say dot, dot, dot. And we'll say Cn is C0 over, because we just look at the pattern. Now, maybe you're not going to be able to just find a pattern like this all the time, right? No, that's probably not true. And it's not necessary that you do, but it's kind of nice when you can. Dot, 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 3n plus 2. So what this means is, of course, when you calculate this, let's say you wanted to calculate C3. Let's see if it works, right? Here's C3. We know what C3 should be. Okay, so C3 would be C0 over 3 factorial. There's the 3 factorial. And then we come over here to 3n, right, plus 2. So 3n plus 2 when n is, so we're doing 3. So n is 3, right? That is 9 plus 2, and that's 11. So that means that's just these first terms, 5, 8, 11. Do you see how that works? So it's not, this, I really shouldn't write a times here because it's not times. That is the formula, right, for the highest term. Okay, so you go 5, 8, and then 11 is the highest term here. The next term would be 14, right? So that's what this tells you. It tells you the highest term in that sequence of multiplications. Okay, what about over here? Well, we have Cn is equal to C0 over n factorial, and then 1 times 4 times 7 times dot, 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 3n minus 2. Again, this gives you the highest term in the sequence of multiplications. Let's check it for C3. So we'll put n equal 3. C3, 3 factorial. Okay, good, there's the 3 factorial. 1 times 4 times 7, right? But 3n minus 2, so this is 9 minus 2 is 7. So we know 7 was the last one, right? Okay, and for C4, it would be, you know, 3 times 4 is 12 minus 2 would be 10. So you'd get this one, right? So this is the last term in this multiplication sequence. That's what this notation means. Okay, so now the funny thing about this is that we have all these terms that just have C0 on them, right? There's no C1 and C0 like we've seen before. So that's a little odd, but that means we can just choose C0 to be something. And why don't we just choose to be 1? Don't choose it to be 0. That would not be good, because then all of your coefficients would be 0. That's a no-no. Okay, but you can certainly choose it to be 1. Okay. So that means when we go back to our series up here, right, we can write down the 2 solutions, the one for r equals 0 and the one for r equals 3. I mean 2/3. Okay, so r equals 0 solution. What do we write down? Well, we look at our series. Okay, well, it's x, so this is the first solution, right? This will give us the y1 of x. All right, so y1 of x is x to the 0, right, which of course would just be 1, and then times C0, that's the first term, but we're choosing that to be 1, right? So we're going to choose, I'll put that down here, choose C0 equal 1. Okay, and so we get 1, and then then we can write the rest as a sum, right? So plus the sum n equal 1 to infinity of our Cn's, which we have a formula for down here, right? With C0 equal 1. And I just get 1 over n factorial 5 times 8 times 11 dot, 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 time, you know, and then 3n plus 2 tells you the highest term in that sequence of stuff, okay? And then times, of course, x to the n. That's the first solution. And for r equal 2/3, right, we have the second solution, y2, and that's x to the 2/3, because it's x to the r, x to the 2/3, and then of course c0, right? c0 x to the 0, so that's just 1, plus our series, sum n equal 1 to infinity, and then we have 1 over n factorial times 1 times 4 times 7 dot dot dot, and the highest level term, and that multiplication of course is 3n minus 2, and then of course we have our x to the n, and that's our second solution. And so the general solution here is going to be y equals some constant, a y1 of x plus b y2 of x. And these constants here, a and b are constants. And I'm just not using c's like we usually do because we have so many c's floating around here, right? Okay, a and b are constants that are chosen, or that are determined by the initial value problem, right? The initial conditions, or boundary conditions, whatever you might have. And notice that they definitely are. They are linearly independent, right? They don't have exactly the same powers floating around. That's what would have to happen, right? Like this would have to be, x squared plus 2 or something. And this would have to be also x squared plus, something else, but not an x. So these are linear independent solutions. Now remember, we can't always get two solutions directly out of this method. That's what the Frobenius theorem says. It says at least one solution you can get that has that form. So good. But we're not guaranteed to get that solution, right? All right. So let's take a look at a little bit more detail into this method, right? So one thing we can do is we can look up here at this equation here, this thing here that tells us R. Remember how we got that, right? That was the page before. Roll back the video if you can't remember. And this thing has a special name. It's called the indicial, or indicial. I call it indicial, and that's because a professor of mine used to call it indicial. But anyway, people probably call it indicial because it looks like that. Okay, this is the indicial equation, or the indicial equation, if you want to use my professor's pronunciation here, that tells you R. Now there's a little bit of a section in your book that goes through how you can derive that without going through all this work, okay? And you can. It doesn't always work exactly the way you want it to work. So I like to point it out, because we're going to use it in an example. But I like to go through the math like we've been doing, right, to get that equation. I just like to actually, just, plug and chug through the math, turn the crank. But there is a sort of a formalism that tells you how to get that indicial equation. I'll try to say it the way everybody else says it. And if you're just given the differential equation. So maybe that saves you a little work. Okay. But again, I like to just turn the crank. Okay. Let's look at that next. I need to get rid of all my layers here that are showing so that we can... There we go. Perfect. Okay. All right. So let's say go back to our initial differential equation, in which we have, y double prime plus p of x, y prime plus q of x, y equals 0, right? Well, if you can write down these little p's and q's, remember how we have little p and q? We have little p of x is equal to x times big P of x. This is big P of x, right? And then we have little q of x is equal to x squared times big Q of x, right? Remember those things? If you can write those down, you most likely will get a form, a general form like this. So P of x, little p is some constant plus a1 times x plus a2 times x squared plus dot dot dot. Now you're not always going to get these coefficients to be non-zero, right? I'm just saying this could be this. You could write it in this form. Some of these coefficients will be 0 depending on P of x. Okay, but Q of x we'll just write similarly, right? As b0 plus b1x plus dot dot dot, or how about we go b2x squared plus dot dot dot, right? So when you put it in this form, then you can actually solve for this indicial equation. And you get r minus 1, and then you get plus a0r plus b0 equals 0. Okay, so this gives you this sort of general formula that you can use to find the indicial equation, which is kind of cool. I mean, like I said, I like to turn the crank, but why not? Let's check. Okay, so if we go back to our previous example, okay, so let's check. So an example we'll just use as our previous example, the previous equation we just solved, right, where we had those two r's, r equal 2/3 and r equals 0. So remember the equation looked like this: 3xy double prime plus y prime, minus y equals 0. That was the original equation. So I'm going to put it in the form that looks like this first. So I get y double prime plus 1 over 3x y prime minus 1 over 3x y equals 0, right? And now this guy is my big P of x, big P of x. And this, of course, is my big Q of x. And now I'm going to find this, this stuff here. So I have little p of x is equal to x times the big P of x. Oops, equals. Why not put an equal sign? Okay. And then that's good. So if we look here, that's just going to be 1 over 3. Now notice in that expansion up here, that means that a0 is 1 over 3 and all the other ones are 0, right? a1 is 0, a2 is 0, etc. So this tells me that a0 equal 1/3. Okay, let's do the little q of x. So little q of x is x squared times big Q of x. And by the way, this equation really only works if you're around a singular point, regular singular point x equals 0, by the way. Regular singular point here, okay? You'd have to make another equation if you were expanding, if you were solving around a different point. Okay, so let's do that x squared big Q of x. So big Q of x is minus 1 over 3x. So x squared times that is just going to be x minus x over 3. Notice up here that means that this term, this is b1, right? So that b1 is minus 1/3. Okay? All right. So, and notice that b1 does not come into the equation for the indicial, right, to this indicial equation. Sorry, it's a little messy up there, isn't it? See if I can box that. This is the indicial equation. Okay. All right, so let's calculate. All right, so we see the indicial equation is r minus 1, plus a0r, and a0 is 1/3. And then plus b0, but we don't have a b0, right? No b0 for my q. Okay. All right. So, and that's, let's just, we're going to, and this is all equal to 0, by the way, right? So I'm going to just mush this around a little bit. I'm going to multiply everybody by 3. So I get 3 and expand, 3r squared minus 3r plus r equals 0. And then I get 3r squared minus 2r equals 0. And I'll write that as r times 3r minus 2 equals 0. And that indeed is the indicial equation we had gotten before. So that's kind of a nice shortcut. I mean, to each his own. If you like to do that, awesome. If you like to turn the crank and just let it sort of happen naturally, awesome as well. Okay, and you can use this as a check, right? So you get some indicial equation, check it by using this method, right? By turning the crank. I mean, turn the crank, get what you think is the indicial equation, check it doing this. Okay, so that's just pointing that out. Let me find where we are in the notes. Okay. Okay, so there's another example in the book where they use this method to get the indicial equation first and then crank through the series. So why don't you go look at that example? Let me see what example it is. Let's see. It is example 3, so check that out. I don't think we need to go through it. It's a nice way, the more of these you do, the better. So go through those examples. All right, let's move on. And what we're going to look at now is that case that we were talking about where you only get one solution, right? Remember the Frobenius theorem, right? Let's take a look at that again. It really only tells you that you are guaranteed to get one of that form. And then you got to do something to get the second one. So sometimes you're just going to get one. All right, let's look at an example of just getting one. And this is the equation xy double prime plus y equals 0. Okay, and let's just go through the exercise of getting the indicial equation. So I'm going to use the fancy method. So we're going to divide through to get everything in the standard form, y double prime plus 1 over xy equals 0. Notice in this case, if we look at this case, we have that p of x, big P of x is 0, right? Because there's nothing proportional to y prime. And so, of course, that means that in that indicial equation where we multiply x, right, so little p of x equal x, big P of x, remember? That is going to give me 0, right? So all the coefficients, those little a's and everything, a0, a1, etc., are all 0. Okay, so fine. What about q, big Q of x? Well, big Q of x is x squared times, sorry, I meant little q. I'm trying to get little q here, not big Q. All right, so little q, so we have little q of x. Okay, so we have little q of x here, and of course that's x squared times big Q of x, and that's just going to give me x times y, or sorry, just x, right, because the Q of x is this thing, sorry, just x. And that looks like, A1 is non-zero, but B1, sorry, B1 is non-zero. And so just to remind you what that looks like, right? So little p of x is A0 plus A1 x plus, right, dot, dot, dot. And little q of x is B0 plus B1 x plus dot, dot, dot. So B1 isn't 0, but B0 is 0. And remember our formula for the indicial equation, let's go back here so I can find it, is r minus 1 plus A0r plus B0. Okay, so we have B0 is 0, we have A0 is 0, and so we know that this is just r. For this particular equation, r minus 1 equals 0 is the indicial equation. All right, well, obviously that's a solution of r equals 0 or r equal 1. Now, I'm not going to go through the math, but I encourage you to sit down with this and substitute a series in here, right, with the method of Frobenius, right? So with this x to the r, right? Now you know what r is, so you can just pick one, like pick the 0 case, go through the series thing, get all your coefficients, go through, and then pick the 1 case, go through the series solution and get all your coefficients. What you're going to find is that all the coefficients are the same for both of these. So no matter which one you pick here, you get the same CNs. Now, obviously, those two situations do not give you two linearly independent solutions, right? It gives you one. You can keep one of them, but it doesn't give you two. And this is the situation in which you got to do something else. But I want to show you that there's kind of these rules that tell you whether you're going to be in that situation, which is cool, given the indicial equation. Okay, so let's take a look at that. And there are 3 cases. So that help you understand what you're going to get out of this. Okay, so what we're going to do is we're going to assume here that when we write R1, we mean the larger of the two. So we're going to have 2 roots, R1 and R2, and let, just for ease, we're just going to let R1 be the larger one. Larger root, unless they're equal. One of the cases is that R1 equals R2, but in that case, that's not the case. We just want to say that for the first 2 cases, we're going to let R1 be the bigger one. All right, so we have case 1. All right, case 1 tells you that if R1 and R2 are different, okay, distinct, okay, and the difference difference R1 minus R2 is not a positive integer. Let me move this guy out of the way. Integer. Then you do get 2 solutions of the Frobenius form. Frobenius, and I forgot how to spell it. Okay. Let's just go with that. All right. Form, right? And that's that series solution, right? Where y of x is x to the r sum n equal 0 to infinity of c n x to the n, right? You're going to get 2 of those. That's what we just, the one example that we just went through had 2, well, okay, so the previous one where we had 2 solutions, right? And that, remember what the r's were for that, right? What were the r's? So those were, remember, so the example where we had r equal 0 and r equal 2/3, right? This is the bigger one. So and call that R1, but 2/3 minus 0 is not a positive integer. So we got those 2 solutions, but that's because we were in case 1 and didn't even know. Okay, let's look at case 2. Gotta go back to my notes here. Case, oh, sorry, 2. All right, hold on. I gotta get back to my place. All right, case 2, where we have R1 and R2 also distinct. Are distinct. And the difference R1 minus R2 is a positive integer, then there exists two linearly independent solutions, but there's a catch, hold on. Two linearly independent solutions but they have the following form. They're not both of that Frobenius form, okay? Like the very first example we did, right? Okay, so they look like this. You get y1 of x that looks like that Frobenius x to the r sum n equals 0 to infinity cn x to the n, right? But then your second one, and this says it also says that cn is not, c0 is not going to be 0 in this case. Okay, and then it says y2 of x is going to look like some constant c times, and that's a capital C, times y1 of x, so that series, times the ln of x. And I hope this doesn't surprise you, because we've seen that we get ln of x's, right, when we're looking for that second linearly independent solution. Okay, but then plus a series part, x to the r2. And that should be x to the r1, sorry, x to the r1. That should make sense, I hope. And this is x to the r2, and then you get a series part, right? That looks like a Frobenius form, and we're just going to call those bn's just to distinguish them, x to the n, okay? With b not equal to 0, and c is a constant. So here's the weird little caveat. C is a constant that could be 0. So this is a weird case, all right? So in the case where we have this case, where we have r1 minus r2 is not a positive integer, we get definitely two Frobenius form equations, right? So two linearly independent Frobenius series type equations, right? Like we saw in our example. But if you have r1 minus r2 is a positive integer, you could end up with two Frobenius form equations, right? You could end up with y1 looking like this, and y2 having c equal to 0 and looking like this, which is Frobenius form, right? So you could get that. But at the very least, you will get one, or sorry, you could get also one that has an ln of x, and then plus this, right? So it's kind of a weird case. You could end up with something that looks just like this case, but then again, you could not. Okay, a little strange. All right, so the last case, let's go to a new layer. Okay, so the last case is so case 3. All right, this is r1 equals r2, you could probably guess. This tells me that a second linearly independent solution, right, will always contain a logarithm. Okay, so second solution, this should say solution here. So remember the case before, so if we go back to that case, turn that off and turn it back on. The case before, we could have a log, but c could be 0, big C, right? But this case tells me that I will always have a log in my second solution. Okay. Okay, right, so the case 3 solutions look like the case 2 solutions, except for that there's always a log term. Okay, so I'll write them down. So we have a Frobenius term, x to the r1 sum n equals 0 to infinity of Cn x to the n, with C0 not being 0. And then the second solution is gonna look like a log plus my other term. So we have y1 of x times the ln of x, and then plus my Frobenius term x to the r2. Well, r2 is equal to r1, but right, you get the point. Maybe I'll just put an r1 here. And then the Frobenius, well, this is a Frobenius term, n equals 0 to infinity b n x to the n. Okay, so that tells you what your solution is going to look like, which is great, because if you go through and turn the crank and get your solution here, right, you do have to do more work to get this part, right, but you will get a log in there. All right. Okay. All right, well, guess what? That is it for Chapter 6. We're not doing Chapter 6.4. And I'm going to mention 6.4 because the whole point of 6.4 is using these series solution methods to solve particular equations that give you things like Bessel functions, the Legendre polynomials, right? Things like what we call special functions. They really shouldn't be called special functions. It should be called named functions or something, as your book points out. But the equations that give you the Hermite polynomials, etc. And those come from series solutions. Okay, the way that the equations that represent the differential equations whose solutions are Bessel functions or Hermite polynomials or Legendre polynomials require series solutions, and that's how you end up with those special functions. So I think it's a cool thing to look at, and probably what you should do is, the first time you ever have to really use one of those, right, which is going to be, those of you in quantum have already sort of used some Hermite polynomials. But then you can go back and look and see how are they derived. It's nice to know, but we're not going to go over it. All right, so that is it for Chapter 6.